Morning Pros, my name is Ivan and I'll be presenting the DDW 2D component for CC03 Group 9. So to start with, our problem statement is how might we estimate the level of moderate and severe food insecurity based on the UN Food and Agriculture Organization's index. So we use the country's GDP per capita, net imports of cereals per capita, and the production of cereals per capita. So rationale is that the country's wealth would affect its food security. Moreover, the amount of imports and food production will also affect the amount of food available in the country. This in turn affects the food security of the country. So we got our data from the FAO stat website and we pre-processed it. So for example, cleaning up the food insecurity data, we had to extract the year and the values, and then we put it all into a data frame. So after extracting all the data that we wanted, we put them all into a single data frame. We merge them all together by the area code and the year. Then afterwards, it's time to create our linear regression model. So for features, we have GDP per capita, food production per capita, and net imports per capita. And the target is the food insecurity index provided by the United Nations Food and Agriculture Organization. So first we plotted GDP per capita against food insecurity, and we got a y equals 1 over x relationship. Then when we plotted food production per capita against food insecurity and net imports per capita against food insecurity, there wasn't a very clear relationship between them. So for our first model, we chose all our features to be linearly correlated with the target. So we split the data into training and test sets. Then we normalized the features. And then we prepared the feature and the target. So we had to account for all the betas from beta 0 to beta 3. Then afterwards, we trained our model on the training set and we tested our model on the test set. So this is a plot of our actual values against our predicted values. So for the first model, our beta is like this. Mean squared error is 270.5. R squared is 0.526. Then for model 2, we chose to take the inverse of GDP per capita, so 1 over x. And this is the plot of inverse of GDP per capita against the food insecurity. So for our second model, we did the steps the same way, and we obtained a better mean squared error of 192 and R squared of 0.66. So for analysis for the first notebook, the first model shows that when GDP, food production, and food imports decrease, the prevalence of moderate and severe food insecurity will increase. The coefficients also imply that production of food is the most significant factor in affecting food insecurity. Hence, we chose to focus it on that in Notebook 2, which Chi-Xiang will be going through. And then we achieve a higher R-square score in the second model, which shows that it's a better fit. Thank you.
In our first model, we found out that the production is the most important factor to affect the food security. In the phase 2, we will introduce which factors affect the production. The variables we choose is education, temperature, emission, area, and population. At first, we read all the necessary fields and download the countries used in phase 1. And then we extract the country's name and find the same countries in all of the files. And then we write a function to select the specific values for the country we selected. And this is a function we write to generate a new column by dividing one with the other. For example, we can calculate population density from the population and divide by land area. Then after prepare all the lists, we create a new data frame and put in all the information after we clean up to form a database for the multiple linear regression. This is our data frame. And then in our first model, we just choose the education, temperature, emission per cap, land area, and population density without any modification. And then this is our result. We can see from the result that the education, temperature, and land area has positive impact on the production, but emission and population density have negative impacts. These results are generally intuitive because high education means more technologies used in agriculture. Then a large land area means more agricultural lands. Then high emission indicates a low efficiency in dealing with the waste, and high population density region requires high density economy instead of agriculture. After the first model, we drove the graphs of all 5 variables against production. We find all the relations are not necessarily being linear. For example, the relationship between education and production per capita is similar to a quadratic relation, and for emission and production it seems to be an inverse relation. And thus, in our second model, we change the education and temperature into education square and temperature square, emission to emission inverse, population density into population density square root of population density. Then after the regression, our R increased from the 0.37 in the first model into 0.48 in the second model, indicates an increase of the precision of our model.
Here's our group's web app about the model. There are 2 parts on the main page. Part 1, Modeling Food Insecurity. We try to find the relationship between the 3 variables and food insecurity respectively. And here's our results and analysis. Part 2, Modeling Production. This is our conclusion and analysis.